In the future, technology will ensure prosperity for everyone, which also means you have got a lot more money to spend on giant space guns. We've discussed some basic concepts of space warfare before, and in the general context of futuristic warfare, you essentially have 4 areas of interest: relatively close combat like infantry, combat in atmospheres or orbits, and interplanetary or interstellar conflicts. Our focus is on interplanetary for today, which differs from fighting on or near a planet because of light lag, which is even more severe for interstellar warfare, and we'll discuss both another time. Because of the time it takes light to travel, conflict timelines get expanded to timescales similar to those of pre-modern naval warfare. Communication takes a long while and travel longer, weeks if not months, and even exchanging fire is likely to be something that takes hours or days, not seconds or minutes. Now that's rule number 1 of warfare. You spend 99% of your time waiting, followed by brief moments of excitement and terror. But in the case of interplanetary warfare, that upgrades to 99.9% thumb twiddling, even when you are actively exchanging fire with someone. We talked a fair amount about that in the original space warfare episode, but our focus was just on the space battle aspect, not the strategic situation, and that probably needs clearing up first. Recently on the channel, we've been looking at colonization of the solar system, focusing on planets, our own moons and asteroids. In science fiction, we often focus on those too, as the major players in any conflict, Earth versus Mars, like we see in the show The Expanse. Great show, but I doubt that will ever happen. For it to happen, space travel has to be abundant and cheap enough for at least tens of millions of people to travel in space every year. Otherwise, there's no real option for conflict. It's not some one-sided conflict like Australia versus all of Eurasia, it's more like Eurasia versus a small, underdeveloped Pacific island. Mars ain't pushing Earth and its billions around with a few million residents. And while sci-fi often likes to present us a resource-strapped, overpopulated Earth versus a more high-tech Martian colony where all the scientists live, Earth is not going to be resource-strapped, see the Ekmanopolis episode. And not all the scientists are going to move to Mars. If you've got space travel cheap enough for mass colonization, you don't have energy shortages, and that means any planet is a ridiculous powerhouse in terms of resources. But more importantly, by the time you've got planets all colonized, you also probably are no longer planet-centered. Even before you get to the Dyson Swarm, Kardashev 2 level of things, you've got hordes of habitats in every rock floating around out there. And there are thousands of them big enough to support an entire modern planetary population and economy for geological timespans. Short form, if you've got interplanetary military conflicts, it is because you have cheap space travel, and that is because you have energy abundance, and if you have energy abundance, every rock in space is a super valuable gold mine that you can turn into a lush, human-friendly environment. So the stage at which such conflicts can begin occurring isn't a few settled planets acting as big superpowers, but rather a period more akin to 1,000 city-states, out around the big colonizable rocky planets of the inner solar system. The dynamics change again as you start shifting towards a Dyson Swarm. Let's start by examining the classic Earth-Mars conflict. It is probably important to know what the heck they are actually fighting over, but we have had a fair number of wars over fairly surprising things. Of course, sometimes the official recorded reasons are bizarre, but the unofficial actual reasons are entirely logical. It is not terribly ethical to invade your neighbor because you want their stuff, but it is decently logical. It generally helps to give a reason like they insulted the king or something, though historically, "we want your stuff" has often been an entirely acceptable official justification for war too. It does not apply to Earth and Mars. I don't know any plausible scenario where Earth wants anything Mars has, not while there is still a moon in the sky and a system population of less than a quadrillion. When you are fighting over raw materials at the planetary scale, it isn't planet-on-planet combat. Each planet is a budding Kardashev 2 civilization that now occupies the region of space the planet did. But fighting for general solar system dominance or trade rights is on the table, and one can always find an excuse. In any event, one of the first issues with attacking another planet in your own solar system is all the space in between the two of you. That distance falls into the scale our brains tend to only comprehend as very large. If you've ever taken a road trip that lasted all day, think of doing that all day every day. You will still die of old age before arriving at another planet, but your grandkids born on the trip might live to set foot on one of the closer planets. Missiles, of course, travel a lot faster, but we can flat out discard any upsized equivalent of an ICBM. No chemically powered rocket can deliver warheads to another planet, not because they can't get there, of course, but rather because the target is going to casually blow every one of them away. They just can't go very fast, and will need to go even slower if we want to save any fuel for maneuvering. And you need that because such missiles are not even a little bit stealthy, so the only way to avoid them getting shot by a laser is if they routinely jink in a random direction, like we discussed in the space warfare episode. You could maybe do it with metallic hydrogen if we can make that a viable fuel, but even that is iffy. So too would be the typical atomic rockets we discussed in the nuclear option. You need a compact and high-powered fusion drive or antimatter for a self-contained interplanetary missile to be a threat. Fortunately, the difference between a missile and a ship is one of them doesn't need to carry fuel to slow down, and also tend to be unmanned, so you can get away with launching one out of a mass driver. This has a downside though, because for missiles to be good weapons when someone has the ability to shoot them down, you need them all to show up at the target or the edge of its anti-missile envelope at the same time, volleys arriving together, not a stream of them like a machine gun. That is the cool thing about modern missiles, they are all self-contained, so you can launch your entire inventory all at once. You don't need to queue them up like bullets in a gun. If you are instead using a launch system like a mass driver to get those missiles up to speed, with their fuel just for maneuvering, you need a launcher for each missile, or they won't come in as a volley. Now at interstellar distances, as we discussed with relativistic kill missiles, you can fire thousands of things once a day, each a little faster than the last, and expect them to arrive on time, like sending a vehicle out on a road trip every minute, with the first traveling 61 miles per hour, the second 62, the third 63, and so on, so they all arrive at the same time. At interplanetary distances and desired speeds, you can still do this trick, but not nearly as well. You are essentially trying to overwhelm a system that's firing as fast as it can recharge and retarget, so the faster your devices are moving, and the more fuel they have to maneuver, the smaller that window of time is. Same reason, you want something that can break into a lot of pieces when it hits that interception envelope. The nice thing though about very fast missiles is they can fragment a lot because they don't need to carry a warhead. Missiles moving several times the speed of sound carry more kinetic energy than would be released by their weight and explosives. Missiles moving at relativistic speeds do as much damage as a nuke would. So this is a basic interplanetary missile. A question then becomes how fast can you throw one initially, and that comes down to two basic maximums, though all sorts of engineering difficulties could limit it more. How fast can the missile accelerate without trashing its guidance system, and how long can you accelerate it, or basically how long your launch track is. Humans can't handle prolonged acceleration of a dozen, much less hundreds of G-forces, but solid metal slugs can handle thousands of times more. They don't have electronics in them. Modern military artillery have electronics in them rated to handle over 15,000 Gs, and you might be able to go higher with better technology, but we'll assume that value at 150,000 meters per second. Length is important in this context. It tells us how long our gun needs to be and also how close the missile can get without being automatically destroyed by anything detecting and shooting at the speed of light. 15,000 Gs might sound remarkable, but it is in the ballpark of many conventional firearms. A barrel length of about a foot or a third of a meter would allow an acceleration only up to about the speed of sound, slower than most guns spit out a bullet. This is one of the reasons trying to put electronics or machinery in normal bullets is harder than folks assume. Final speed rises with the square root of length, so a barrel 100 times longer, 30 meters, gives you the square root of 100 or 10 times the velocity. 3,000 meters, 100 times the velocity, 30 kilometers a second. 300 kilometers and 300 kms, 0.1% light speed. You need a track length of 30,000 kilometers to get to 1% of light speed, and 3 million for 10%. Those are obviously ridiculously long gun lengths, but keep in mind length is ambiguous here. You might be pushing on it with lasers after it leaves the gun for more speed, or the barrel might be a simple thin mesh of superconducting wire you shot out right before shooting the missile. And it's not really that each missile needs its own launcher as it needs its own power supply. On the interception end, we've got two factors. First, how quickly the missile is moving, and second, how quickly it can randomly accelerate in a given direction to jink. For any given combination of missile speed, size, and acceleration rate, you have a window of space and time you can shoot it and be sure to hit with a laser. See the Space Warfare episode for details on that, but all things being equal, you want the smallest, fastest, and most maneuverable missile you can build, and anything moving less than 0.1% of light speed probably isn't even worth shooting at interplanetary ranges, because any orbital defense laser is going to get many shots at it while it is in the no-miss automatic kill envelope. Of course, that envelope size depends on the missile size and acceleration, but if all it can carry is chemical fuel, even if it can pull off that full 15,000 G burn, it won't be able to do that for even a second. We often see individual rocket fuels listed by their exhaust velocity or ISP, specific impulse, listed in seconds. Loosely speaking, an ISP is how many seconds a rocket made almost entirely of fuel can accelerate at 1 G, meaning if it burned everything up in 1/100th of a second, it would be several meters off course, survive a shot, then get blown away by the next because it can't maneuver anymore. Size helps too, but you also need your missile a certain size for electronics and thrusters, and building smaller than an intercepting laser beam's width doesn't help either. Small cross-section also helps, narrow and long, but they might get side shots at it too. Now your missile is going to shatter into hundreds of smaller and harder to hit fragments right before it hits the confirmed kill envelope, and is not aimed at the actual planet anyway. You are targeting all those orbital lasers with your first wave, so atmospheric entry isn't as big an issue. You can't kill those with lasers from way back at Orth or the Moon because they can pull the same trick of jinking around, only a lot easier. Your moonside launcher is too big for that, and it's very long, and any major damage along the length of it is going to wreck it, at least until you can repair the damaged sections. Now this is an oversimplified case, because not only can Mars field a ton of defensive satellites in low orbit, they can have them up in high orbits, and they can also keep more mobile platforms along the path to Orth. They can also defend with big atomic bombs along the way too, not just lasers. Or normal bombs. It doesn't take a very large piece of shrapnel to kill a relativistic missile, and the corridor for them to travel down isn't very high. The missiles can't really sweep around in a wide arc. Unlike a normal spacecraft going to Mars, which doesn't follow anything like a straight line, these are moving pretty close to straight and can't deviate from that much. So by and large, Mars knows where the attack is coming from, and can litter the path with defensive countermeasures to deal with the attack long before it gets to their home. This is an important point, one we'll examine more in a bit, and indeed that is rule number 1 of warfare. Always do your fighting far from home. That way less of your stuff gets broken. A few questions have probably come up in your mind by now. What if we have a better drive system for our rockets, genuinely compact high-efficiency fusion, or even antimatter? What if we go for higher acceleration rates by making dumb munitions, just metal with no guidance package that higher accelerations would crush? Or why aren't they using lasers or particle beams on or near Earth to attack directly? And the answer is, you might, for all of the above. Each has their problems though. My goal today isn't to tell us how these conflicts will happen, I have no idea, but rather to point out some of the options on the table and the flaws in some of the other known ones. Fusion, except as a bomb, is always likely to be rather slow, allowing high final speeds, but not fast quick burns of thousands of Gs. You could get around this partially by going the bomb route and firing warheads behind you to push you along with their explosions, but that's unlikely to provide super fast acceleration either, and means sending a very large platform full of missiles that way that fires them once you're up to speed and closer to the destination. Antimatter circumvents this. It is the ultimate rocket fuel, and makes for great warheads even at relativistic speeds, but manufacture and storage of it is hard and dangerous, and that's when you are just worried about regular storage in peacetime. Shoot a nuke or a fusion reactor and you kill it, it doesn't explode, so someone can attack your munitions storage without causing huge amounts of damage. Shoot an antimatter storage facility and it will all explode, releasing even more damage than when they would have hit a target, since they will use a lot of that as fuel during the flight. You might be able to get around that by storing it far from anything of value, but more on that in a moment too. For particle beams, those are pretty dubious at long range because they will start to spread out, and they are very susceptible to magnetic fields. The same for lasers, and both will have problems doing more than sheer heat damage to anything planet-side when they arrive already diffused and then have to go through an atmosphere. They cannot maneuver en route, so placing anything along their path, which is exactly predictable, ends the threat. The same is true of big dumb bullets, except they travel slower. Now a planet is a big object, but a planet-sized object, or collection of objects, does not have to be massive. Mars has a cross-section of 36 trillion square meters. A sheet of aluminum foil 1/10 of a millimeter thick masses 27 grams per square meter, so it would weigh about 1 trillion kilograms. That's hardly light, but it's minuscule compared to planets. We've discussed doing stuff like this to make solar mirrors or shades for terraforming purposes before. It might be rather hard to get a laser through a patch of space composed of thin balloons full of hydrogen that formed a bubble wall with the components shifting around. Scale plays tricks on the mind, but throwing 1-ton missiles at relativistic speeds costs a ton of energy, as does powering some huge particle beam or laser, and defense like this could literally consist of tiny bullets composed inside of nothing but a compressed gas container and the thinnest foil you can make, so that when the container pops it expands into basically a soap bubble. Space is a vacuum. It takes very little gas to inflate something relatively large. Rather than point defense on a ship or space station that fires off conventional explosives, it might fire these bubble bullets instead. They are also one of the handier ways to clear space debris from orbit. You could have guns that fire these bubble bullets into the right places to intercept something, or fill holes in a bubble wall. Call them bubble guns. Bubble guns. So at interplanetary ranges, you want smart weapons moving as fast as you can get them, and they may even need to include their own countermeasures to jink around debris or clear a path the same way. Again, you'd probably go with waves of volleys, thousands or millions of weapons coming in a reasonably tight pack. In terms of time, not distance, you do want them spread out a bit, each wave following and tailored to the expected defenses. So the Interplanetary War begins somewhere in the middle of the disputants, rather than it just being empty space stuff goes through unimpeded. Now as we mentioned, you've got that narrow corridor between planets that attack can come from, but I also mentioned you don't want to keep your antimatter anywhere near there if you've got it. More to the point, a big focus of this channel is on how solar system colonization is not just planets, and that indeed they tend to become increasingly smaller in terms of the portion of the system population they make up as time goes on. People are going to be building homes in asteroids, literally inside them, since excavating asteroids is easy, and even if you are mining them intensively, that takes a long time and probably would not involve exporting everything, just the most valuable minerals refined down. Both Earth and Mars are surrounded by the asteroid belt, which is wide, full of millions of decent-sized objects, and spread out. The bigger ones probably host very large colonies, and the smaller ones are great small outposts. One of these big mass driver or missile launchers we discussed might be as long as a planet is wide, but they are still thin, and you could spool one up like a ball of yarn and pack it into a fairly small asteroid. Just so long as you can unwind and deploy it faster than the light from it can get to the target and back, carrying an attack laser. It makes a handy missile launcher on an unexpected vector. You could also probably hide one on a cargo ship, and this is assuming you even feel the need to hide it and don't just have big battleships carrying them around. You can also make such things single-use devices. a very flimsy launcher inflated by a nuclear explosion or series of nuclear explosions that also provides the push and power for the launch. Nukes are hard to tap for power, that's why we don't just use fusion bombs to run our own energy grid these days. And we could, by the way, build a very large water tank big enough to handle an H-bomb blast and let the steam generated turn turbines. It's just huge, and H-bombs aren't exactly cheap. But again, nukes are hard to tap for energy, and using the blast for one to power a mass driver or laser for a single shot is an option. That trick, if you can make it work, allows you to send missiles that get as close as they can then fire, shoot out gamma-ray lasers or grazer blasts, or a relativistic slug out of some very thin and long mass driver that is inflated by the blasts. Either way, when the conflict is no longer just two planets, but thousands of various colonies too, either provinces of one of those planets or independent city-states or confederations, a lot of the dynamics change because you don't just have one vector to defend against anymore. Personally, I would not expect a united Earth versus a united Mars versus a united asteroid belt, but rather something like India and Australia, their Martian colony at Olympus Mons, and their 50 asteroid habitats going to war with, say, Egypt, Ethiopia, Madagascar, Indonesia, and its Martian territory, and their various asteroid habitats over control of geostationary space above the Indian Ocean. We might see early colonization of the solar system done by groups of various nations working together, but once it gets decently cheap and routine, those colonies are generally going to emerge from one place and rely on that country for a lot of support, either as a territory, a state, or a sovereign ally. You might get folks on Mars feeling like they have more in common with each other than their home countries, but in a place like the asteroid belt, you are as far or further from most of each other than from Earth. And while we see shared oppression and grievances often given to asteroid miners as a reason to revolt, that is just fiction borrowing from history. Any sci-fi setting where you hear about water shortages or air recycling issues either needs to qualify that with not enough water to terraform this planet, or it's full of it. If you have spaceships operating under Newtonian physics, any single one of those big cargo haulers we see has a power plant capable of running a modern continent's electric grid. They are not short of energy for recycling water and air. They are also probably not breaking their backs and minds somewhere, since first of all, low gravity helps with that, and second, almost all the work is probably being done by robots anyway. But, people being people, they are not likely to ever be short of grievances with their neighbors or homeworld, but it's unlikely to be because the asteroid mining colonies have folks falling over dead from exhaustion, suffocation, dehydration, etc. More likely they'd be complaining about how Country X was inflating or deflating the price of titanium or something. In that sort of context, where you probably have lots of cultural and economic allies on the same planet the folks you dislike are from, and a lot more neutral third parties, hurling crustbuster nuclear ordnance at them is probably not on the table. Things get even worse in that regard as you progress towards a Dyson sphere or Dyson Swarm. See that episode and the Kardashev scale episode for more details on how those actually form and operate. But in short form, you would tend to have billions or trillions of large rotating habitats, many physically connected to each other, and a slew of ancillary facilities all packed around the sun. Except they aren't packed, because even though a completed Dyson swarm is supposed to block out all the light from the sun, it's not so much a thin shell as a thick cloud or fog composed of many islands separated far apart, some by themselves, some forming into archipelagos that move together, but all moving relative to the other swarm members so that many people near you today are not next month. All the same weapons and defenses apply, but you can probably be way closer to deploy them just from the sheer amount of stuff helping you hide it. However, you probably can't shoot stuff as fast either, because you do have billions or trillions of habitats involved, most of whom, even nearby a conflict, have no skin in the game. At least not till some reckless ass fires and misses the target and splashes some previously neutral third party. And that's rule number one of warfare: avoid helping your enemy recruit people. We often think of Dyson swarms as jam-packed. They are not, and composed of fairly flimsy structures, which they probably are not. your typical rotating habitat is probably only a small portion of the overall habitat, and is probably crammed inside some hardened, non-rotating superstructure composed of meters-thick armor of diamond-hard thin tanks full of cheap hydrogen as filler. It's probably got huge arrays of cheap thin solar panels around it to eat up munitions, and backup fusion power to run on. It's probably got most of its food grown in flimsy low-grav habitats nearby. It's probably got the entire outside slathered in point defense lasers, and those bubble guns and tons of outposts further away with the same. And it's got all those neighbors, who will not appreciate megatons of diamond-hard shards flying off into space, and at them, while you pound away at a habitat that isn't so much a fragile egg or luxury cruise liner as a giant battleship with nice interior decorating. When you've got the kind of energy supplies and automation to be building these things cheap enough for folks to own suburban homes on them in the first place, bet on the architects and marketing guys including "and it's got tons of armor and defense" in the brochure, along with how good the local schools are. Traditionally, countries tend to spend at least 1% of their economy on defense even in peace times, often a lot more. We'd like to think in the future we will be more peaceful, and I think we will, but it is worth remembering just how much ordnance 1% is in a post-scarcity civilization building these kinds of things, and also that a post-scarcity civilization can get away with spending a higher percentage of their GDP on defense too. It's also quite possible that if you get inside one of these rotating habitats to invade it, you won't be facing a regular or civilian population, since it is entirely possible a regular civilian in a high-tech civilization is a transhuman with light-speed reflexes, centuries of skills, and a backup copy of their mind somewhere that gives them license to take risks. But we'll discuss stuff like boarding actions, dropships, and orbital bombardments another time. We have no idea how war will be fought in the future, or if it will be more or less common than now, if it will be more civilized or tend to go for scorched earth strategies. Indeed, often you see the most no-hordes barred combat from civilizations that don't fight much, so conflicts might be rare but all-encompassing and brutal. Personally, I think we won't see many armed conflicts in the future. I certainly hope so. But while we had to do a lot of guesswork today, we have hopefully painted a more realistic picture of what interplanetary conflicts would be like. We'll look at interstellar ones another time too. Next week, we will be visiting Venus in our second installment of the Outward Bound series, Colonizing Venus, and we'll take a deeper look at terraforming. For alerts when those and other episodes come out, make sure to subscribe to the channel. If you enjoyed this episode, hit the like button and share it with others. Until next time, thanks for watching and have a great week.